Good morning, everyone. Welcome to STEM in the Kitchen. We're excited to have some more fun with our friend Lori Bone from the Longway Planetarium. Morning, Lori.
Hello.
Hi. Just a note to everyone that we do have links to the handouts and as today's survey. Thanks to the Institute of Museum and Library Services, we're able to offer these really fun, engaging webinars for you this month. So please take a minute to jot down those links and make sure that you fill out that survey at the end. So without further ado, I'm going to stop sharing my screen. I'm also going to put the links in the chat box here for everyone. And Lori, if you'd like to take it away, I'm going to give you the hosting powers.
All right. I always feel so important when I get the hosting powers. How's everybody today? Hope everybody's doing well and staying healthy and safe and trying to get through this time together. I'm so glad to be a part of this training this morning. So our goal today is to explore matter with hands-on science activities that use common kitchen materials. I'm going to provide easy-to-use activities that you can in turn use with your visitors. They can be done virtually like we're going to do today. They can be used face-to-face, either in small group or when we can come back together. I know you're missing your visitors every bit as much as we're missing ours. These activities are correlated to the next generation science standards. So the activities that we're doing help support what kids are doing in their classrooms. So that's just a way to kind of support those needs for kids while they're out of their classrooms. So an overview of the setup for this webinar today, I'm going to provide a brief background about matter, the science concept. I'm going to give a short overview of the next generation science standards. I have short video clips of demonstrations of these activities with time for questions, answers, clarification, discussion. The materials or the activity sheets and the NGSS correlation are in a Google Drive folder that's been shared out with you. There's also a document on there with links to the YouTube videos that we created to demonstrate the activities. So that information, all of it will be available to you in that folder. My contact information is in there as well. Please feel free to reach out if there's anything that I can do to support you while you're working with your kids remotely. All right. How does that sound? Are we sounding pretty good? I've got all your wonderful pictures and I'm so glad for it. Sounded okay? Okay. So let's get into some background about matter. This is kind of the very quick skim level of this concept. So matter is anything that takes up space and has mass. Anything that takes up space and has mass. So take a look at I have a little washcloth here, a little towel, right? Does this towel take up space? Let me ask you a different way. You see my finger and this towel? Can my finger and this towel be in exactly the same space at the same time? They can't, right? My finger will push the towel out of the way because this towel is made out of stuff and so is my finger. My finger and this towel, that stuff, can't be in the same place at the same time. Matter takes up space and it has mass. It's made out of something. It's different than energy, things like heat or light, okay? Takes up space and has mass. It makes up all the stuff around us. The air, the table, the chair I'm sitting on. All matter are made out of tiny particles called atoms, okay? Each element on the periodic table, right? Let me hold this up here. I didn't share this one. Each element on here is a different type of matter. And these elements combine in different ways to make different types of matter with different properties, okay? So these combinations of these elements, these atoms, get together and form different types of materials with useful properties. And we can manipulate the way these things combine to make things that we want, make life easier. If you're interested, material science is a really interesting field of science that where they manipulate materials to make properties that are useful to us. Now, molecules are the smallest unit of substance that you can have with that substance still retaining the property, okay? So a molecule of water, if I had a glass of water and I cut that glass of water in half, cut that water in half, and then I took that half and I cut it in half again, and half and half and half, till I get down to the last piece of water, the last molecule of H2O. If I break that down any farther, I won't have water anymore. I'll have 2 hydrogens and an oxygen, okay? A molecule is the smallest unit of that matter that I can have without taking away its properties. Now, property is the characteristic of a substance. It describes the substance, and properties can be physical or they can be chemical. So a physical property would be size, shape, color, odor, melting point, freezing point. A chemical property talks about things like reactivity, flammability. So one of the properties of matter are the states of matter, how I find it. And we all know it, right? It's a solid, a liquid, or a gas. And your 4th graders are going to say, and plasma, right? We don't have plasma here on Earth, okay? It's kind of a sun thing. It's plasma is heated beyond a gas. There's a 5th one they're talking about called the Bose-Einstein, and that state of matter is super, super cold. Okay, so solids, liquids, and gases. Solids have a definite shape and a definite volume. Okay, so I have this rock, right? This big rock. And my rock has its own shape. No matter what I do to this rock, if I hold it this way, this way, this way, hold it on my head, the shape stays the same. And so does the size. Okay, it has a definite shape and a definite volume. Volume is just a math thing. It talks about how much space it takes up. I have a liquid, okay? Liquids have an indefinite shape, but a definite volume. So I have this little flask with some blue water in it. If I tilt the flask, I can change the shape of the liquid, right? But the volume is still the same. I have about 175 milliliters of water in this flask. If I tip it, I still have 175 milliliters, right? The volume didn't change, but the shape does. And I have this solid, right? I have a balloon. And I put gas inside. Now, does the gas take up space? It's kind of tricky, isn't it? It does. It takes up space. I know this because it's pushing out the sides of the balloon. Okay? Gases take up space and they have mass. They're made out of something. Now, your little kids will go, what are you talking about? It's made out of something. I can't see it, right? It's invisible. But I can feel it on my face, can't you? Right? There's something there. I can't see it, but I can watch it push the clouds across the sky and I can see it flutter the leaves, okay? So gases are matter too. They take up space and they have mass. Now, we are going to be thinking about, later in our time together, we're going to be thinking about how atoms move in a solid, a liquid, and a gas, okay? And this is called the particle theory of matter. Now, we said that matter is made out of atoms. We are going to pretend, and I'm going to tilt my screen down so you can see what I've got on the table here. We're going to pretend that the beads inside this Petri dish, see, I've got a few beads in this Petri dish. Can we pretend that those are atoms? Okay, so I have just a few atoms in this one, and I have a little bit more in this one, and I have a lot of atoms in this one. Okay, can we see that okay? Okay, the one with the atoms that are tightly packed, we're going to call this a solid. And if I shake this around, you're going to notice that the atoms move. They shake back and forth, don't they? But they're not really tumbling over each other and changing positions. They're packed so tightly, they can only move just a little bit. They just kind of vibrate, okay? Liquids are spaced out farther. By the way, remember our solids don't change their shape? Doesn't that make sense when you think about how those atoms move? How they're so tightly packed and they just vibrate? How can they change their shape? Liquids are more spaced out. you can see that when I move them, they've got a little more room to move, but notice how they just kind of slide back and forth, right? Liquids can change their shapes as well, or as liquids can change their shape. Now, this one is gas, and there's a lot of space between these atoms, and these atoms move all over the place in the petri dish as I slide these things around. Where the liquids can just kind of go back and forth and up and down, these guys are all over the place, okay? Now, when I change something from a solid to a liquid to a gas, what I do, I have a solid and I add heat, and these beads, these atoms, get moving around really fast and they're able to melt. They spread out, they start moving more quickly. As I evaporate that liquid and it becomes a gas, those molecules, those atoms again spread out and start moving faster. What do you suppose is going to happen when I take this gas and I cool it? I remove heat energy. When I do that, they slow down, start taking up less space, and they condense and become a liquid. If I take this liquid and remove heat energy, those atoms slow down, take up less space, and become a solid. Okay. So that was a really quick talk through matter. How are we feeling about that, okay? Any questions before we start? I should have mentioned Kathy's going to be monitoring the chat box. So if you have any questions or comments, do feel free to jump in that chat box and she'll let me know so we can stop and get anything answered if we need to, okay? All right. So very quickly, let me go ahead and share my screen for a second. I'm going to jump on here and I'm going to show you this. This is part of the next generation science standards. This is not the whole thing for matter and its interactions. I took out these foundation boxes: science and engineering practices, disciplinary core ideas, and cross-cutting concepts. Now, I'm not sure how familiar you are with this, and I don't want to belabor it if it's something that you know about, but very quickly, in the NGSS, there's another box on top that are called the performance expectations, and those are kind of the assessable questions. That's what students are expected to know at the end of each grade. Below these three boxes are the connection boxes. So it takes these standards and connects them to other places in the NGSS, and it also connects it to English language arts and math and social studies, if I'm not mistaken. So really quickly, we're going to focus on these three foundation boxes. Science and engineering practices talk about the doing of science, okay, how you set up an investigation, how you pose a good question, how you collect data. It's the doing, the verb of science. The disciplinary core idea is kind of the meat and potatoes. It's what you're learning about. And the cross-cutting concepts are big ideas, really big ideas that are pertinent across every grade level, K through 12, and they're also pertinent through any discipline of science, whether it be life science, earth science, or physical science. So cross-cutting concepts are these really big ideas. The idea behind next generation science standards is that there are these three foundations or three strands that work in concert with each other. So in order to teach a good science investigation, you're not just focusing on the what of science and reading the content, and you're not just focusing on the doing. You're focusing on the whole aspect of how science is and what science needs to be. So in second grade, these standards that we're doing today land in second and fifth grade. The standards today, the DCI, the disciplinary core idea, we're talking about different kinds of matter existing. They can be solid or liquid depending on the temperature. They can be described and classified by observable properties. Different properties are suited to different purposes, and a great variety of objects can be built up from a small set of pieces. Also, heating and cooling can change a substance. Sometimes those changes can be reversible, but sometimes those changes change what something is made out of, and there's no way to change it back. For 5th grade, we're going to be focusing on, come on down here, matter of any type can be subdivided into particles that are too small to see, but even though then we still know they exist and they can be detected by other means. The model that shows that gases are made from matter, particles that are too small to see and moving freely in space. Matter is conserved when it changes form. And measurement of a variety of properties can be used to identify materials. So when we're thinking about how this relates to the school day, these are the standards that are going to help you kind of get your mind around that. As far as we're concerned, being in an informal education, we usually have these standards right next to us while we're developing activities. While we're not bound to these, we're not assessing and that, we still know that it's good science, and it helps me make sure that what I'm doing is age appropriate and kids have some kind of connection to them if they've been following these standards in their classroom. That's why I really like to be familiar with these standards and have them around while I'm developing activities, even for an informal setting. All right. Let's go ahead and get into our first activity. So, welcome to bubbles and surface tension. And we'll be right back. Here you go.
Hey, Lori, the sound isn't.
Okay, let me grab that. I thought I had that set.
Yeah, it worked earlier.
It did, we tested it. Oh boy. All right, here we go. Let me back that up.
The same type of bubble. Let's find out some more about how bubbles work. Before you understand about bubbles, you need to think about surface tension. Surface tension is a force that holds droplets of water together. So, for this activity, you'll need a piece of waxed paper or a styrofoam plate. A glass plate would work, or a glass bowl, but you need a slippery type of surface. You're going to take a dropper and you need some water. You can add a little bit of food coloring if you have it so that the droplets are easier to see. You need a dropper. I have these in my classroom, but if you don't have a dropper, you can just use a straw. To use the straw as a dropper, just slide the straw into the water, put your thumb over the opening, hold that thumb over the opening and lift it up. Can you see the colored water inside the straw? Hold it above the surface and then drop. With a little bit of practice, you can control the sizes of drops that you make. You can make big ones and little ones. But you're going to take this and you're going to make water drops. Can you make a great big one? Let's make a great big water drop. Can you see that shape? Look at this water drop here. Can you see this nice dome? Especially if you look at it from the side, you can see that there's a dome. And watch what happens to the shape when I add more water. The water drop's getting bigger, but the dome shape remains. This shape, this dome shape, is caused by surface tension. Did you know that water is sticky? Water molecules attract each other. So they pull together. Remember in our forces webinar, we talked about forces being a push or pull. Well, those molecules attract each other. They exert a pull force. Now, the water inside the droplet, it's getting pulled from the top, the water molecules on top, from the bottom, from the sides. It's getting pulled all around. But the layer on the very top of this thing, this dome, is only being pulled from the bottom and from the sides, isn't it? It's not being pulled from the top. And that's what forms that beautiful dome shape. Surface tension is just that attraction of water molecules pulling each other together. I made that water drop bigger by adding more, but it kept the same shape. So I'm wondering what would happen if I put water drops right next to each other. Right, and I'm going to make them so that they touch. What happens? Oh, did you see how that water drop just kind of reached out and grabbed the other and just kind of took it right in? You can really see that surface tension acting. We put them together. Can you take them apart? Is there any way to make these, take this big water droplet and turn it into a small? Look how that water just kind of clings to each other. Isn't that surprising? I'm going to take this plate and I'm going to shake. Look at all those water droplets now. Can I push them back together? Oh, look at that. I'm going to take that one and just push it right into that water. See this big drop right here? Look what happens when I add a little bit of soap. I got some dish soap. Just a little bit on the tip of a toothpick, and watch what happens when I dip that in. Did you see that just break that water droplet right apart? I'm just barely touching the surface with that soap, and it just makes those domes go splat. I wonder why that is. What happens when you make bubble juice? You take water and you add some soap. The soap molecules get in between the water molecules and they lessen the surface tension. Because they get in between, that force between those molecules aren't so strong, and it allows those water molecules to stretch out. So as I'm blowing air into the bubble, it allows that film to stretch in a way that I couldn't do with just water. Making the bubble solution. There are recipes all over the place. You can get online and find all kinds of recipes. I've added one of the recipes to your activity sheet. I would suggest use Dawn or Joy. Those brands seem to work better. A lot of the recipes that you'll see will call for glycerin. Don't use glycerin. It's expensive and it's hard to get. You have to go to a pharmacy to get it. I would really suggest you just use light corn syrup. It's much, much less expensive and it works fine. The corn syrup slows evaporation, okay? Evaporation kills bubbles. So as the water evaporates away from the bubble, that's what makes it pop. So using the corn syrup will slow that evaporation so that your bubbles can last longer. I went ahead and made some bubble juice, and I have it right here in a tray. Putting it in a nice tray like this on a cookie sheet that's got higher sides, a pie pan, it's a great surface to blow bubbles on too. And you know what, for that matter, you can just take some bubble juice and put it right out on your kitchen table. Just lay it right out on the table surface. It's easy to clean, and then you'll have a nice smelling clean table when you're done. Really easy to use inside. So when you go to blow your bubbles, all you have to do is take a straw, dip the end, and blow. Now, when you blow that bubble, you're going to notice lots of swirling colors. I don't know if you can see this on the video, but they're beautiful. I don't know if you've ever stopped to pay attention to that. But as you let the bubble sit, you're going to watch those colors swirl around, and then they're going to break into bands of color. And what's happening is that gravity, remember that force we talked about, that pull force, gravity is pulling down on that bubble liquid. Oh, there it goes. And as it does, it gets thinner at the top and thicker at the bottom. And light coming through that bubble is being, those waves are interfering, and it's creating that beautiful color that we can see. The differing levels of thickness determine what color that you see on the bubble. You think you can put a bubble inside there? Here's the thing. Anything that's wet can go through a bubble. So I'm going to get my straw wet, the sides of my straw. I'm going to dip it, and I'm going to poke it right through there. I'm going to put a bubble right inside there. I'm going to see if I can put one inside that one. Oh, it fell out. Did you see how it just dropped right out of there? Ah, did it again. Anyway, you're going to help your kids understand how hard to blow. I always tell our students that we blow like a mouse would whisper. Just a little blow. Big blows don't work. So let me show you some of my favorite bubble tools that we use here in our classroom. Anything that you can get wet and has holes in it, you can use for a bubble tool. Okay? So, for example, I bought new measuring cups, and this was the little plastic clip that held them together. So I'm just going to get that wet. It's a nice little bubble. Don't forget straws. Look at this little wire basket we have in our classroom. Anything like this works really well. I love this one. I just got flexible straws and I banded a bunch of them together and poked the straws out in different directions. Just drop that in your bubble juice. How fun is that? You could take a water bottle and cut off the end. And don't forget your hands. Make an O with your thumb and your pinky finger, or your thumb and your pointer finger. How about that one? Watch this. What if happens if I get my hand wet and I grab a straw and put that bubble right on my hand? I'm going to get my other hand wet and stretch it. Your hands are really fun to play bubbles with. Now, if you use your hands, be careful not to rub your eyes. Okay, just learning how to use a straw, and they're really proud of their new skill of just being able to use a straw. And they know how to use it. You put it in your mouth and you suck it up. You suck up the liquid, right? We don't want them to suck, we want them to blow, okay? And they're gonna have a hard time with that. So one of the things that you can do is take your straw, grab a pair of scissors, and at the top of the straw, just cut yourself a little notch. Like a little diamond-shaped notch. Doesn't have to be anything fancy, okay? But if you cut a little notch out of the straw, you can blow, but you can't suck, okay? So you don't end up with a kid with a mouth full of bubble solution. I can still blow bubbles. I got a length of yarn, okay? It's about a meter. Size really doesn't matter, but you want it about, a yard or a meter. And I'm going to put 2 straws on this yarn. Okay, 2 straws on a piece of yarn. And I'm just going to tie the yarn shut. Make a frame. I'm going to pull that around so that the knot's hidden inside one of the straws, and I have that shape. Okay? Now, I'm going to get it all wet. This from the floor. Get it all wet. I'm going to hold my straws together. I'm going to pull them apart. You see my bubble film with those beautiful colors? And I'm going to drag that bubble film Did you see all that liquid fall down when that bubble popped? Be careful, because when you get these to work really well and they start to drift off across the sky, your kid's gonna chase them, okay, which is fun. But the problem is they're looking up at it and it pops and they get soap solution down in their eyes. So be careful, watch out for that one. Now I know what you're thinking, you're saying, Lori, that's a hot mess down there, look at that. And if I do that in my house or inside, it's gonna be really slippery. And didn't you tell me I could put this out on my kitchen table cleaning? That's gonna be a mess. I will tell you this, to make it easy to clean up, just pour a little vinegar on it. The vinegar kind of cuts the soap, or the soap acts on the vinegar, and it makes it a lot easier to clean up. So just pour a little vinegar in there when you go to clean that up. For heaven's sakes, don't use more soap. I actually did that once. I added detergent to the towels I cleaned this up with and had a soapy mess, so watch out for that. If you were with us for the last webinar, the Forces webinar, we did some talking about air resistance, about drag. Remember, we were thinking about how the bottle buggy moved through the air. We were thinking about how air can slow things down and it resists motion. Did you notice as we were pulling that bubble film through the air, could you see the air pushing the bubble film out? What a great example of air resistance and how air is something. There are molecules there that push against surfaces. It's a great example of air resistance or drag.
All right. So, are we good? Were we able to hear that okay? I was afraid the volume was a little low. Is that true? Okay. Okay, thank you. I was worried about that. We don't have really sophisticated equipment yet to do this. It's on the list to buy so that we can do more of this. All right, bubbles are so much fun. We've had bubble festivals here before. One of the things that I would suggest, there are so many different bubble recipes. Play around with it. And in fact, if you've got the time, invite your families to play around with it. See if they can change the amount of soap versus corn syrup versus water to make their own bubble recipe. The thing is, though, for it to be science, they're going to need to write a procedure because they're going to have to be able to share what works really well with other people. Bubble juice does work better if it's aged. If you let it sit for a few days, it really works a lot better. Mine was about 2 days old. Could have worked better than it did. I will say this, the recipe that I used is for a very small batch. I normally make mine like 4 gallons at a time. I was really surprised at the amount of corn syrup they suggested to use. I mean, it was a lot compared to what I usually use. And what I found is that it ends up making chunky bubbles. Now, they were thick, and I don't know how else to explain that other than they just kind of seemed like bubbles, right? If you're looking for the kind of bubble that's just going to float across the sky, this is probably not the recipe for you because these bubbles just tend to go right to the ground. So there's definitely a lot of engineering and making around this idea of creating your own bubble juice that you could certainly get into. All right, let's go ahead and take a look at our next video. We're going to do ice cube races.
As we talked about in the introduction, matter, anything that takes up space and has mass, is made out of molecules. And those molecules are in motion. Solids, liquids, and gases are. So we're going to take a solid and we're going to change it to a liquid because we're thinking about those molecules. So I have 2 pieces of ice and I'm going to put these pieces of ice down here and watch what happens to them. We're going to try very hard not to let it melt. So think cold thoughts, polar bears, penguins, just not in the same place because they don't belong together. And wow, what do you see happening? I noticed that this one is melting very, very quickly. Can you see it going from a solid to a liquid? I noticed that this one, the only liquid that's on there is the liquid that was here from the ice cube sitting out. It doesn't seem to be melting at all. I wonder why that is. What makes ice melt anyway? Do you think there are ways that you can manipulate the speed in which ice melts? What kind of tools could you use to make the ice melt? For this, I bought these, they're called melting blocks from Educational Innovations. And while they look the same, you think that they're the same thing, they're actually not. This one is made out of foam. Listen, this one, heavier, it's made out of aluminum. The aluminum transfers heat very efficiently into the ice cube and makes it melt, while the foam insulates. So, what can we do to manipulate the rate of melting? Melting happens when you add heat and matter goes from a solid to a liquid, okay? So what you're actually doing is using heat to speed those molecules up. So, for ice cube races, what you can do is get a partner, get 2 pieces of ice. You want them to be about as same as you can get them. You want to control that variable, don't you? You don't want you to have a small piece and your partner to have a big piece, although if I had a smaller piece, I bet it would melt faster. And we want to figure out how to make our ice cube melt faster. We are going to make sure that we're doing some measurements around this because we need to kind of track our process to see which one is melting faster. And there are a lot of different ways to weigh things or to measure things, aren't there? There's weight. So if I had a kitchen scale, I could weigh these. We, in our classroom, have digital scales. We could weigh those ice cubes and see how close they are in weight. Are there any other ways that you could think of to figure out how heavy these things are? Do you have any way to make a balance of some sort? that might give you an idea? Another way we can measure is by length or width. In your Google folder that I'm going to share with you, I attached a printable with 6-inch rulers. They have both the standard measurement and the metric measurement. You can print these off. I just use packing tape to laminate them. So I could certainly use these to measure the length of my ice cube. I'm going to make sure that I start with the widest part, and I'm also going to make sure that when I use my ruler, I start right at that line underneath 0 instead of at the end of the white. And I'm going to measure, it's about 5 centimeters long. Okay, so I can measure that way. If you don't have a ruler or don't have access to a printer, what other materials do you have around the house that you can use as a non-standard measuring device? Here in the classroom, we have craft sticks. And I could lay that across there and use a pen and mark each time I measure how much smaller my ice cube's getting. I've got these little wooden cubes that we picked up at the dollar store. I wonder how many wooden cubes across this ice cube would be. It's 3 wooden cubes across. I wonder how long it would take until it's 2 wooden cubes across, or 1 wooden cube across. Maybe I could predict that. Another thing I could use to measure length or width is just a piece of string or yarn. I can use it that way and cut it. I can wrap it around so I get the whole size all the way around. Another way of measuring is time. How long does it take for the ice cube to melt? So for ice cube race, what I'm trying to do is to get my ice cube to melt faster than my partner's ice cube. What can I do to make that happen? What sources of heat can I apply to make this melt more quickly? I could probably breathe on it. My breath is warm. I could probably hold it in my hand as long as I could. I have a hairdryer at home. I could use a hairdryer on mine. Could run it outside in the sunshine. It's a beautiful day today. Put it out in the sun and see if the sun could melt it. What other ways could you think of melting it? I have another way that we may be able to melt ice. I mixed up some salt water. Didn't measure. I just took some water and added some salt, stirred it up. So let's see if we can make this melt our ice more quickly. I'm going to use a dropper again. You could certainly use a straw. Let's pour that on there and see what happens. So I noticed that it was a little hard to see when I was pouring that salt water over the ice cubes, so I decided to add a little food coloring to see if it made it easier. A little bit. And I'm just going to keep adding that salt water and see if that makes my ice cube melt faster. What happens is that salt water has a lower freezing temperature than regular water. That means it's got to get colder in order for salt water to freeze. Because I'm turning this into salt water, it's making my regular water ice cube melt. It's actually melting quite quickly. I wonder if there are any other kinds of household materials that you could use the same way. I wonder if baking soda would work this way. Or sugar. I wonder if sugar would make the salt melt. I wonder if there are any other types of household materials that I could use that make my ice cube melt more quickly. We can't very well measure the water, can we? Because to see how much this ice cube has melted, because I've been adding water to it. But can you see this little groove it's made in the ice? It's actually melting a lot faster. There's a good chunk of it gone compared to this piece right here. So you can see that salt water is making the ice cube melt more quickly.
Okay. Why am I not finding you?
Your stop share down at the bottom.
Where are you? I cannot even find my stop share. What in the world?
Oh, you got to go out of full screen maybe? Are you out? Yeah.
There you are. Okay. There we go. There we go. Sorry about that. All right. So as we were thinking about different ways to melt that ice, we were making it go from a solid to a liquid by adding different forms of heat. One of the things that we did a while ago, we used to have a water party in the summer at our museum, and we'd invite kids to wear swimsuits and towels, and they got to play with hoses and whatever. We ended up making big ice cubes for them. We used a Dixie cup, we froze it halfway, and then we put little gifts inside of it, little rings or toy dinosaurs, little bouncy balls. We ended up, and then we put water on top and froze it so the little prize was on the inside. And we gave each kid one of these ice cubes outside and said, well, it's your job to see how fast you can get it out. And the strategies that they were coming up with to try to get that toy out of the ice were amazing. They were throwing it down on the concrete, trying to get it to break. I found one little girl who had found a piece of asphalt, and she found a puddle of water that the sun had been shining on. And she realized that that puddle of water was quite warm. And she was just rolling that back and forth to make it melt. They were really coming up with really great strategies for getting that ice to melt quickly. All right, so I'm keeping an eye on the time, and it is going ever so rapidly like it always does. So I think we're going to go on to.
We can give you a little extra time if you need it.
Can you really?
Yeah.
I'm sorry, I do this every time. I have so much fun, I just can't stop. Let's go on and look at liquid exploration. So we're going to take a look at liquids now. So let's pull this video up. Again, all these links are right here in your folder.
Dissolve more clearly, and you want to get this as clear. Let's take a just like the air, the molecules are in motion in the liquid. So I have three different types. I have cold water, I have hot water, and I have salt water. To prepare the salt water, I just dumped in some salt and stirred it until it dissolved, until it completely dissolved. Any kind of salt will do, but kosher salt tends to dissolve more clearly, and you want to get this as clear as you can. I don't have a measurement for how much salt to add. You just want to keep adding salt until it completely dissolves. You want as much salt as you can get into the liquid without having salt left over at the bottom. So I also need some food coloring. What I'm going to do is I'm going to put 3 drops of food coloring into each one of these, and we're going to see, we're going to watch how the food coloring spreads, and we're going to see if there's a difference between the 3 types of liquids. So here we go. This is the cold water. 1, 2, 3. So you can see that that's moving down towards the bottom of the cup and spreading out. It's still kind of falling down. Let's try the hot water. Ready? 1, 2, 3. Does that seem to be moving more quickly? It seems to be spreading out faster than the cold water. Why would that be? It's because the molecules in the hot water are moving more quickly than the molecules in the cold water, and making that food coloring spread out through the water more quickly. Now let's try the salt water. 1, 2, 3. Wait, what? That's not spreading out at all. In fact, the piece that did fall down seems to be going back up to the top. Why would that happen? Well, I mentioned that this was salt water. And remember, matter takes up space and it has mass, and salt is matter. As I dissolved that salt into the liquid, it's taking up space inside there. And it's taking up space that the food coloring can't move through. So if you think about the molecules of the salt dispersed in that water, taking the place that this food coloring would have taken, you can see why it just kind of sits right on top. Again, I'd play around with other types of liquids. How fast does it move through some of the things that you can find in your house? How fast would it move through cooking oil? Will it move through cooking oil at all? Are there other types of liquids that you could find? I wonder what would happen if I took some water outside and put it in the sun. I wonder how long it would take to make it spread out by heating it by the sun. What other ways can you think of to make this liquid move the food coloring through more quickly?
Okay. One of the things after I made this video, it occurred to me that I think it would have been more effective had I not labeled the cups. I really wished I would have just left them alone and then just showed the phenomena and invited people to try to figure out what was happening. If I were to do this again, I think that's the way I would go. And if I were to do this with kids, I'd definitely do that way as well, because it's really interesting to to see the ideas that they come up with. If I tell them, all right, this is all water, I did something to this one, something to this one, and something to this one. What do you think it could be? That invitation to thinking is very, very important in science. Answer, they'll get there. But inviting them to really think deeply about what's going on in that water as it's moving that food coloring through is important. So we've watched solids melt and become liquids. We've seen liquids, and we've watched how hot liquids, those atoms are moving more quickly, and we watched it spread that through. So the next thing I'd like to look at are gases. So let me show you this video.
Okay, this is the collapsing bottle. So I have a pop bottle. Individual size will work, or 2 liter, doesn't really matter. What you're going to do is put some hot water in the bottle. I filled it, I don't know, maybe 1/3 of the way up. The trick for this is to make the water as hot as you can without actually shrinking the bottle. You can't use boiling water. Boiling water gets the plastic so hot that it shrinks, and it ruins the effect for this demonstration. So the trick is to get it as hot as you can get it without melting the bottle, and yet still hot enough to make this happen. So I've got hot water here, and of course we know this bottle isn't empty from the top of the water to the top of the bottle. There's something there, right? It's air, okay? And air is matter, it takes up space, and it has mass. Remember, these molecules are moving quickly, these molecules are moving. So remember, this bottle is made of matter. The plastic is a solid. Of course, we have liquid water in the bottom, and we have air between the top of the liquid and the top of the bottle. Now, we know that hot water will evaporate, right? It'll go from a liquid to a gas. So I'm going to take this very hot water and I'm going to put it into some ice water. I'm just going to put that bottle in there. I'm going to put it in the ice water, and we're going to see what happens to that bottle. We're just going to leave it there. We're not going to touch the lid. I do have it capped very tightly. And we're just going to watch what happens. This activity is for demonstration purposes only. It involves boiling water and poses a safety hazard for kids, so this is an adult-led demonstration only. So let's crush a can. We're going to use air pressure to smash this can. So I have a little bit of water in the bottom of the can, and I put it on the hot plate, and now it's boiling. Can you see the steam coming out of the opening? Can you hear it? I've got a pretty rapid boil going on inside the can. Now what I'm going to do is I'm going to use these tongs, and I'm going to flip this can over into some ice water. Let's watch what happens. those molecules of the liquid and the gas inside the can, and think about their motion and how the motion was changing, how it changed as we went from boiling the water to turning this can upside down, that's important, and putting it into the ice cold water. What do you think happened? So as the water was boiling, it was evaporating. It was going from a liquid to a gas. And that means that those molecules in that liquid got moving so fast that they were able to escape that attraction. Remember the liquid, the attraction between the water molecules we talked about, and change from a liquid to a gas. So we had gas in here. And also remember that that hot gas is not as dense as the air around it. So it rises and it leaves the can. Now when I turned this upside down and I put that hole inside the water didn't go inside the can. It plugged that hole, and as that water vapor and the air inside the can cooled, those molecules started moving more slowly, less pressure on the inside, meaning more pressure on the outside. And that's why our can smashed the way it did. If we go back to our collapsing bottle, you can see the sides have smashed in, and the longer I let this sit here, the farther those sides are going to smash. Is there less matter inside the bottle? Did anything leave the bottle? I mean, how could it? There was a lid on top of the bottle. So the amount of matter that's inside the bottle stayed the same. But it's a matter of, though, as the air cools inside the bottle, it has less pressure. Those molecules aren't moving around as fast. They're not hitting the surface of the bottle quite as hard. Lower pressure on the inside, higher pressure on the outside means that the air pressure is going to create a force that pushes the bottle in and makes it collapse the way you see it here. Now this did take a few minutes, probably 6, 7, 8 minutes to get it to really start smashing down pretty well. So this is a good one to start, do something else, and then come back to it. Keep an eye on it. It'd be a great opportunity to record data as well. I would have the kids measure the amount of water that I put inside the bottle, and when it's done collapsing, I'd have them measure it again, just to see that we didn't lose any appreciable amount of water. I would definitely be tracking the time as well. In fact, you could put a chart up and design a chart to show, to keep track of the time. What do you suppose will happen when I crack the lid and open the bottle? Do you think it'll stay the same? Do you think it'll stay smashed, or do you think it'll push back out? Think about the air pressure. Let's try and see. Oh, did you see it push back out? Went right back to its same shape. When I opened the lid, I let air in there and the air pressure evened out, so it went back to its original size.
All right. Air pressure is a fun thing to play with. In fact, I probably could have done an hour with that by itself. That's really quite a fun one. And I am going to say I'm going to call dibs, because we're taking our Harry Potter themed summer program online this summer, and I think I'm going to use that one, because that was actually quite fun. All right, so it looks like we have about 6 minutes left. I have a video that's about 7.5 minutes. Would you like to continue? Are we good? All right.
Yeah, if a few people have to leave, just be aware that we are recording this, so you can come back and watch the recording later.
And if you have to leave, thank you so much for stopping by this morning. I hope you found some useful things. So let me just go ahead and show you this last video. We're going to make some mystery bottles.
those molecules move. If they're solids, they just kind of vibrate. If they're liquids, got a little more motion, and then gases are just singing all over the place. I want to think about molecules in terms of density. Now, density is a middle school concept, okay? Kids aren't going to get right down into the nitty-gritty of how density works until 6th, 7th, or 8th grade. Your youngers are going to think about this in terms of sink or float. Some things stay on the top of liquids, some things fall to the bottom. I'd like to just clarify density, the concept of density, before we get into our activity. Density does not equal weight, okay? People say all the time, oh, heavy things sink, light things float. That's not exactly true. Just because something is heavy doesn't mean it's not going to float. Density talks about the amount of molecules being packed into a certain space, okay? If I had a suitcase and I was going to Disney World and I had an empty suitcase to bring back all my souvenirs, on the way down to Florida, that suitcase would not be very dense. There wouldn't be very many molecules inside that suitcase. That suitcase is this big, okay? On the way back though, I got my Mickey Mouse ears, I got 3-day-old churros, I got all these little things, and I packed that. My suitcase is so full I have to sit on it to get it to close. Same amount of space? Absolutely. More molecules inside? Yup. Density talks about how molecules are packed together in a given amount of space, okay? So we're gonna play around with some sink and float things. So I've got 3 different liquids here. I have some water, I have the leftover corn syrup from Bubbles, and I've got some oil. I'm gonna use a measuring cup, and a funnel would be good. Notice that I'm gonna do this inside of a tray because my hands spill quite frequently, and little hands spill too. So for this activity, you're gonna wanna do this in either outdoors or in some kind of container that can catch spills. What I'm going to do is add these 3 liquids to a bottle, and I'm just using a soda bottle. So I'm going to use about a half cup, but I only have a 1 cup measuring cup right now, so I'm going to have to do some math here to estimate how much is a half cup. So I'm going to add a half cup of water, pour that into a funnel. Okay. I put the water in first. Actually, I'm going to go ahead and add another half cup. I think we've got room to add a whole cup in here. Okay, so put the water in first. Water's at the bottom. Okay, I think I'll go ahead and add the corn syrup second. Now this one I am only going to use a half cup. So I'm pouring, watch how that pours. It's really thick, isn't it? Pour that out. So I'm going to pour this really slowly into the bottle, and let's see what happens. I'm pouring this in second, okay? Water in first, so it's on the bottom. Corn syrup is going in second, so it should probably be on the top, right? So I'm going to point the funnel, the end of the funnel at the side of the bottle, and I'm just going to gently pour that in. You can see the kind of the bubbly corn syrup at the bottom and the water on the top. Wait a minute, I put the water in first. It should be on the bottom. Let's try some cooking oil. Let's see what happens with cooking oil. Now, at the planetarium, we tend to buy the bigger bottles, and obviously little hands are going to have a hard time manipulating this big bottle. So what we do is take a pop bottle or a smaller size container and transfer the oil into the smaller container so it's easier for little ones to pour. But as they're pouring, you know that oil's going to slop down the side of the bottle, and it's going to make the bottle really slippery. So I just add rubber bands down the side to make little grippers for the bottles so little hands can hold on to them more easily. Now, I've got corn syrup on the bottom and I have water on the top, even though I did put water on first, and I'm still a little miffed about that. So I'm going to add cooking oil next. It's a nice yellow color, isn't it? So I'm going to add a cup of cooking oil. Corn syrup on the bottom, water in the middle, and cooking oil on the top. What do you suppose is going to happen if I turn my bottle upside down? Turn it kind of gently. Corn syrup is still on the bottom, water is still in the middle, and the cooking oil is still on top. No matter which way I turn that bottle, it's the same. Corn syrup on bottom, water in the middle, and cooking oil on top. That's because the molecules that make up the corn syrup are tightly packed. A lot of molecules in a little bit of space. They're more tightly packed than the water. They're more tightly packed than the cooking oil too. Can you find something, an object, that when you put it in the bottle, it will float on all three of these layers? What would that look like? Can you find an object that can fall through or sink through all three of these layers? What would that look like? Floating would be on the top, sinking would be on the bottom. So here's the tricky part, and it is tricky. Can you find an object that will sink in cooking oil but float on water? Sink through the cooking oil but float on the water. Where would you find that in this bottle if you can find something that does that? It would sink through the cooking oil, but it would float on the water, and you'd find it right at this layer here. I wonder if you could find something that could sink through the cooking oil, sink through the water, but float on the corn syrup. What other materials can you find? What other liquids do you have around the house that you may be able to add to this bottle? Here's another way to do this. You could get sugar, get several cups of water, same amount in each cup, but add different amounts of sugar to each one. You may want to color each layer with a different color. And if you're really careful and you add that water so that it just drips down the side of the cup, you should be able to stack the water, the sugar water, according to its density. The water that you add the most sugar to will be on the bottom. So the most sugar molecules there packed into that same amount of space. The least amount of sugar will be the layer on the top. This is the book I love to use with Sink and Float. It's called Who Sank the Boat by Pamela Allen. It's about a donkey, a cow, a sheep, a pig, and a mouse. And they all decided to go out for a row in their boat. And one of them, the last one in, sank the boat. I'm not going to tell you.
So I'm not going to tell you who sank the boat, but it was surprising. And kids are like, wait a minute. It's a great little book. Okay. Mystery bottles are really fun, especially when you get into the floating and sinking of it. That can get messy. In my opinion, it's not the measurements that really matter. Putting measuring tools in kids' hands and giving them the opportunity to try to measure things and understand how important it is to be very careful when they pour. Spills don't matter. The important part for this are the measuring skills and the pouring skills. So measurements, we give them so that they can practice, but they, we're not going to sweat over spills. All right, all of that material is in the Google folder that Kathy shared, along with my contact information. So if there's anything I can do to help you with the science that you're doing, don't hesitate to give me a call. I'd be happy to talk to you. So with that, I'm just a few minutes over. If you have any questions, is there anything I can clarify?
Lori, there was one question in the chat with the water. Can you color the liquids to do that? And then I think going a step further, like to tell the sugar waters apart, would food coloring help with that?
When you do the sugar water, it's important to use a different color with each with each cup of sugar. This one's really tricky. When you pour it, you've got to pour it ever so gently. You need to let it slide down the side, and you need to make sure it's in a transparent cup, a clear cup. So coloring the water is a really important step because you won't be able to see, like you could with the oil and the water and the corn syrup, you won't be able to see those layers if you don't color them. So you're going to need to add a different food coloring. I wouldn't try too many layers, honestly. I would keep to maybe 4 at the most. This one is kind of tricky, but that's okay because perseverance is a part of science. If it doesn't work, we can always try it again.
Wonderful. Thank you. Any other questions in the chat, folks? I think everyone here can agree with me that we all learned a few things today.
Great. Awesome.
That was a lot of fun.
Chemistry is my favorite. I love it. It's really interesting to me how you can take sodium on that periodic table, sodium, which is in that first column, highly reactive with water. You put it in water and it explodes. I mean, it's fun, but you know, dangerous. And you take chlorine that's all the way over on the other side, and it's a poisonous gas, right? This one can hurt you, this one can hurt you. You put them together, and I put it on my French fries. It's table salt. I mean, that's crazy to me. I love chemistry. So interesting.
And we love you, Lori. Thank you so much.
Thank you so much. It's so good to see everybody, and I do hope you have a great summer.
Yeah, we're looking forward to it. Definitely. Do you mind giving me hosting duties back? And I'm going to share our screen.
I'm having too much fun hosting myself.
Thank you so much.
You bet.
And I think we've got some fabulous plans for summer, right, everybody? Lots of great ideas.
All right.
Lots of fun stuff.
See, Kathy Moore, make host. There you go. I'm passing the baton.
Thank you.
All yours.
Awesome. I'm just going to share the screen. Please take a moment to fill out the survey. You can access all the handouts in the Google Doc. And Lori informed us with the motion webinar as well. You can use these handouts and these video links if you'd like, but we encourage you to make your own and promote your own STEM in the kitchen from your library. So thank you so much. Everybody have a good one.